let's start. So usually, I love to start with some introduction about machine learning AI, but for you guys, I know that you are very much aware of what the technology is about. So I'll skip this section, but I'd rather start by saying a few words about what sometimes we see, right? Some people thinking that the brain is actually a computer, or would a computer equipped with machine learning AI mimic the brain? And again, I won't spend too much time on that because the goal of today is to share with you a decade journey implementing machine learning AI for networking. But still, because I'm passionate about neuroscience, I would like to spend just a few minutes with you on that. So it started off basically with the famous Hamon Ikajal, one of the best neuroscientists we ever had, who got the Nobel Prize in 1906. With Camille Golgi. They were not good friends, by the way, but they have a very different approach of neuroscience, especially because Cajal believed in what was called the neuron doctrine. Golgi, thought differently, but he came up with an amazing technology to do staining, right? So in other words, to color some neurons that was used quite a bit by Hamon Ikajal. So what have we learned over the last century? Well, we know a bit more about the brain. What is really interesting is that, of course, we know we have many more knowledge. Still, we now realize that we don't know that much about the brain itself. There are a lot of neurons, about 85 billion. Actually, you also have other type of cells than the neurons in the brain, extremely important. And even just in the cortex, by the way, you've got 17 billion. So you look at these numbers and you start to realize that we barely scratch the surface to understand what the brain is about. So wiring is very complex. Here, I'm just showing you some diagram of the wiring in the brain, what we call the white matter. And we're using DTI techniques to look at that, but these networks are extremely complex. And there are actually multiple networks. Here, I'm just showing a few of them. Like the visual, the somato-motor core network, and things like that. We now know much better about brain networks, and they have a really interesting topology that in many ways could resemble to the internet. We have what we call rich club organization with some major nodes, and we now know that these nodes are heavily involved in some neurodegenerative disease, for example. We know more about what is called the DMN, the default mode network, which is basically the network active when you don't do anything. And we know that the amount of energy spent when you don't do anything special is almost as big as when you do an active task. So I won't go into all that stuff, but what I wanted to say, though, is when you look at machine learning and deep learning, right, we do see a lot of people who believe that we are mimicking the brain. As a matter of fact, and you can find a lot of material from this phenomenal neuroscientist, Bruno Olshausen, on vision especially, who mentioned, and he's totally right, that the model of a neuron has not evolved so much over the past 20, 30 years. We change the activation function, obviously. We try to mimic a bit more what a neuron is doing. But if you look at deep neural nets, they are still the same model of each neuron. And you try now to compare that with a biological neuron. And as a matter of fact, biological neurons are way more complex. So I just want to zoom in for a second. Here you see multiple layers of the cortex. We have about 6 layers. We know that some neurons, they are interconnected across layers and they communicate laterally as well. And we have multiple mechanisms for the communication between all these neurons in a few millimeters of thickness of the cortex. And really, if you zoom in, right, and you look at each of these neurons, there are many, many types of neurons. What you see is here, I'm just showing you some types of neurons you find in the middle temporal gyrus at multiple layers. Look at the complexity of this kind of neuron. and look at the type of neuron we are using when we're doing machine learning or deep neural nets, right? We are far away from the complexity of a biological neuron. Actually, we know now how to model the mechanism of a neuron where you have multiple synapses. And with cable theory, we can actually model the behavior when basically you start to get some input signal, and then they are processed at the soma, which is the body of the cell, and then propagates along an axon. And we know fairly well how to model the behavior. But even at the scope of a synapse now, which is where two neurons will interconnect, look at the machinery. The machinery is extremely complex. And there are communication, there are electrical synapses, we have chemical synapses, and the type of chemicals, which is known as the neurotransmitter, there are actually hundreds of neurotransmitters. So, and you can imagine that for a single cell, sometimes you could have dozens of thousands of synapses. So if you get a single neuron, as I said, you may have thousands of input signals that are processed within a single neuron. And then that neuron will itself spike, send an electrical impulse to other neurons. And these neurons are basically, we have about 85 billion of them, right? And they are organized with multiple networks. So now, when you bear that in mind, you do understand why, even with deep neural nets, with oversimplified model of a neuron, we're far from mimicking the brain. That's basically what I wanted to say. When you look at AI and the brain, some people believe that the current machine learning algorithm, they can sort of mimic how the brain works for vision, for the auditory, which we know a bit less about when you compare to vision, by the way, for language with the Wernicke area and the Broca areas and stuff like that. But others do believe that we're far from that. And I also believe that we're extremely far from it. Even if you look at vision, which is something we really understand now, how it is being processed, or we believe we understand, it's not like a feed-forward mechanism where you do the inference. For example, you trigger some inference of neural networks that we use for vision, for example. This is extremely different, especially because you have feedback loops and stuff like that. So again, I'm not going to go through all of the details, but the bottom line to me is that there's a big debate, right, on what is intelligence. Personally, I believe that this has nothing to do with what we usually refer as intelligence, at least as of today, right? There's no common sense, which is something that is learned by a human, right? There's no generalization. We all know that most of our algorithms, they are really good at performing a very narrow tasks, and there's no real adaptation, right? So that's really another issue when you compare to human intelligence or even animal intelligence. What I believe is that intelligence refers to the ability to model the world around us and explain and understand and imagine. And I would refer you to one of these articles, or in general, there are many, many amazing neuroscientists such as Josh Tenenbaum, who's done amazing stuff in this area. But still, does that mean that ML AI is not useful? Of course not. Machine learning AI is extremely useful for completing a number of tasks. And my goal today is to walk you through what we've been doing at Cisco in this area of machine learning AI for a network. All right, so let's talk about networking for a second. So that's going to be a complete different direction from what I said today. Here, I'm just trying to show you how much of telemetry we get from a network. So networks are complex. Here, I'm just trying to show you a broad range of networking gears, such as the mobile clients, access point with the wireless, or wireless LAN controllers. And then you have the WAN, which is really what the internet is about. We've got network services. We have many ways to get an address with DHCP to figure out the IP address of a site with DNS and stuff like that. Each of these elements will provide you a broad range of telemetry, right? So you can get, for example, the location, the posture of a device, many ways to do some authentication. You may have some information about the utilization of a link, about the traffic, about the type of application being used, and all these things. And I could easily spend 10 hours just going through the single slide to explain this rich, very rich telemetry. The reason why I wanted to spend a few minutes on telemetry is my strong advice would be spend most of your time trying to look at the quality of the telemetry. Some people, and many people, there's a tendency, if you will, to jump on the algorithm, because this is really the fun part, is when you try to look at the objective function, what you're trying to achieve, you have a very rich data set, and immediately you jump on it and you start doing some tuning of the algorithm just to see if you could learn and stuff like that. Don't go do that. Really start with the telemetry. Yes, incorrect telemetry does happen. It could be because of, bugs sometimes in software. There's no software without bugs. It could be sometimes that the telemetry is missing, so you need to handle missing data. In other words, when you run your machine learning algorithm. So there are many challenges like that. And some KPIs are very easy to interpret. If you look at CPU link utilization, for example, on a laptop, we know how to interpret it. You still need to understand how you compute the metric, but it's not something very hard to do. For other ones, it may be a bit harder to even interpret because the KPI may be extremely noisy. If you look at the jitter, for example, in networking, it tends to be very noisy. And this is not because of the quality of the KPI and how you measure it. This is because of the fundamental nature of networks. In this area, you may have some noisy telemetry, and you may want to use some filtering mechanism to denoise the KPI itself. All right. I love this slide. You know why? Because, and again, we won't spend an hour on this one, but maybe stats becomes your best friend. And in many cases, what I've seen in the past was that we tend again to jump to machine learning, which of course we love here at Cisco, but using statistics may be just what you need. And just playing with some, very, very common metrics and variables, such as the percentile and all those things, it may give you a lot of information about what's going on, and it may allow you to model the nature of a variable you're observing, and with that, you may be able to do a lot of things without even a machine learning algorithm on that. Stat models, that's the same thing. So here I'm showing you the latency. So for example, for the internet, I'll go back to that in a few minutes, but in the internet, we look at the delay between 2 points, looking at millions of points, and this is what we call the latency. So in this case, we could see that it was very easy to model with a GMM, Gaussian mixture model. If you look at the packet loss, it was more like a beta model, and that's extremely clear, right? So when you look at that property, using a statistical model will give you a lot of information about anomalies, for example. So if you look at anomaly detection, which is one of the most common use case, yes, indeed, you can use autoencoders, you can use many, many technologies with machine learning, but sometimes stats is really the good way to start. So now let me share with you almost 10 years, as I said before, of actual use cases and how we have used, we've been using machine learning AI through the past decade to improve networking. So that's going to be a very fast, I have to go through a decade, right, in about 40 minutes, but let me show you what we did. So we started off with the Internet of Things, simply because we could not send the telemetry over 4G links, for example. So in this case, the problem was, yes, we could use machine learning in a big data center, but I need to find a way to process the data on a box. And the traditional techniques were too heavy, if you will. So we had to look at machine learning like Bayesian networks for routing optimization, some ANN at the time. It was not a deep neural net, but it was an artificial neural net, a very much simpler model for detecting DDoS attacks. Then we looked at what was known as self-learning networks. I'll go back to this, but this is mostly about security and how we can detect zero-day attacks. And then we moved on again to something completely different, and that was the use of machine learning AI for wireless networks. Then we started to go back to security and say, how can I use ML AI for the device classification? So in other words, you have a device coming on the network. How can I use ML AI to help understand the type of device and detect also spoofing attack detection? And the last but not least is what we call now the predictive internet. I've been working with my team on this project for about 2 years. And we just started to explain a bit what the predictive internet was about. I believe this is going to be a game changer for the internet. And I truly believe that. And I've been in the networking industry for 30 years. I've seen some major paradigm shift. I think this one is really a big one. So I'll tell you more about it at the end of the session. Okay, so let's talk a little bit about the detection of zero-day attacks. So remember, we are in 2013. But the situation has not changed. We still see many, many types of attacks, many types of malware, very sophisticated attacks. Here I was mentioning about fast flux service networks and DGA and tunneling. We still see a lot of tunneling mechanisms here, peer-to-peer protocols, steganography, and stuff like that. Again, I won't go through all of these types of attacks, but every attack becomes even more sophisticated, and security is at top of mind for Cisco. We block billions of attacks every day, and this is one of the top priorities for the company to provide the best services in terms of networking with security. So in this case, I just wanted to show you what we did, because I believe it was a very interesting technology. So in this case, imagine a network with potentially thousands of branch offices. So what you're trying to do is to detect what we call a zero-day attack. So this is an attack for which you don't have a signature. And so we used to have a lot of firewalls, and there are many more advanced techniques now. But basically, we used to basically have a mechanism so that we can inspect the traffic and send some rules and identify signatures and recognize some malware. The problem in this case was to say, I don't want to export a massive amount of data, and I also want to have a mechanism online that will look at the traffic, determine a baseline, and basically be capable of saying, well, I want to recognize an attack like data exfiltration, even though I may not have a signature for this type of attack. So what we did, everything was onboarded on-premise. That's what we call on-premise sometimes, so on a router with a few hundred of megabytes of memory and very lightweight CPU. We managed to do a combined package where we would look at all of the traffic with a technology called NetFlow. Then we would automatically recognize multiple types of devices, locally attached, if you will, on the local network to the router. For each of them, start to do some modeling, and the modeling would be looking at the time of the day, the type of traffic, all these things. So in other words, do some statistical models and machine learning models, detect some anomalies, define the ones that were the most promising, and then use a budget, because the WAN cannot have infinite budget. So the idea was, can I start exporting this data across the WAN? And how do I decide if this anomaly was indeed a security threat? And what I loved about this one is, and we know that as machine learning scientists, it's difficult to have a ground truth. Here, there was no ground truth, because by definition, the goal was to detect zero-day attacks. So there was no pre-existing signature, if you will. And it was an amazing success, an amazing technology. And in this case, remember, it was a massively distributed approach where each machine learning algorithm would be trained online with limited resources, would be able to detect some attacks, share the knowledge between multiple routers. So that's something that was successfully deployed in many networks at large scale. In 2016, we wanted to look at wireless networks. Why? And I'm sure you guys know a little bit about wireless. It could be fairly complicated to troubleshoot. Wi-Fi is a great technology, but again, it could be a little bit complicated sometimes. And so there was a lack of visibility at the time about the user experience and the end-to-end experience as well. Everything was based on naive rules where you would look at multiple KPIs, and then you would put a threshold, and then when you cross the threshold, you raise an alarm, and then it was very difficult to do root cause analysis and correlation and stuff like that. And there was no really good understanding about complex patterns. So our idea was, well, maybe in contrast with the previous project, we could gather this massive amount of data, send that anonymized to the cloud, hosting our machine learning AI platform, and then do some learning so that we can start detecting some issues and cut down the noise. Because again, you never know how to set the threshold, and you want to make it completely dynamic at the same time. We also wanted to do automatic root cause analysis. And this is exactly what we did. So in this case, really one of the biggest problem is, when users complain about the bad throughput, for example, how do you determine what is a good throughput and what is a bad throughput? And the approach before was basically to use a threshold. But again, how do you set the threshold? It depends on the noise in your building. It depends on the size of the uplink. It depends on many parameters, the number of users and the time of the day and many things like that. So the idea was, well, can I use a machine learning algorithm to redetermine when I should be concerned about the throughput? So in this particular case, before jumping on it, we thought, can we determine whether there might be a good threshold that could be applicable to the number of variables we want to observe. So for example, I was mentioning about the throughput, but it's not just the throughput. So when you join a Wi-Fi network, there are many tasks you need to go through in terms of authentication and things like that before you can start joining the network. And this is called the onboarding time. Here, I'm showing you a graph that shows basically for multiple users and customers, what is the average time it takes to join the network. For some of them, as you can see, they are close to 500 milliseconds. For other ones, they are close to 4 seconds. Why? Well, there could be many reasons why the time to join the network is different. It could be because your authentication server is far out. It could be because of a link being congested. There could be many, many issues like that. So what you see clearly is that you cannot find a good threshold, and you need to learn. And that's exactly what we did. So we came up with something called Cisco AI Network Analytics. And this platform is capable of cognitive issue detection and analysis. You can use it also for trend and insights, and also for comparative analytics. So this is how machine learning was used on the platform. So here, this is just a short diagram showing you what I'm talking about. So in this case, this is the average onboarding time, exactly the variable I was talking about. And here what you see, the green band shows you what is the expected normal. On that one, we use a regression and percentile using gradient boosted trees. And that's why you've got 2 bands, and we use the scale factors as well to be on the safe side. And the blue is the actual values. So when the blue steps out of the green band, it's obviously because you have some anomalies. What is difficult, I can tell you, is not really to compute the band, is really to adjust the band so that your system is not too sensitive. And at the same time, not to make it too broad so that you don't miss some important issues, right? It's absolutely always the same issue, and the tension between precision and recall, although in this case, it was not really about classification exercise, but you see what I'm trying to say here. So that was an example. So now, instead of trying to set a threshold for dozens of variables, we started to use machine learning complex models that were capable of looking at dozens of input parameters and then compute automatically the band of what is supposed to be normal. according to that graph, you see that when you start to step out, then you raise some anomalies. And of course, based on the anomaly, you want to understand also what the root cause was about. So really, when you look at that system, the first layer was really about gathering the telemetry. As I said before, prune the data so that you have good telemetry, be able to live in an environment where telemetry may be missing, because that can happen for many reasons. Then compute your models, do root cause analysis. And among all of these layers, I can tell you that this one, the root cause analysis, was really the hardest one, because there's always a confusion between correlation and causation. And I can show you so many examples where the algorithm would basically show you very strong correlation using some Pearson coefficient or other techniques. You would look at that, and as an expert, you would immediately say, no, that's not at all the root cause. It is actually the consequence of the issue, and that's not really the root cause. And then we added a mechanism so that you can have some relevance learning. And people talk a lot about reinforcement learning. Here, there was a notion of reinforcement learning, but not using exactly the same technology, so that the user could basically say, oh, this is really something of interest to me, because there's some subjective part with the user. And we did some very interesting experiments showing some anomalies to a group of users and see the percentage of time they would agree with each other on what was a good anomaly versus a bad anomaly. And guess what? The bad news is we would not always agree on what is good versus bad. So we decided to have a mechanism so that we can learn what was of interest for a group of users for a given customer. And then we could be able to do some dynamic filtering of anomalies of interest, which is sometimes very hard to do, because especially when you deal with security, which is not this case here, if you start to penalize the system for providing a given type of anomaly, and you may hide the real attack in between. And so that's why this kind of feedback loop needs to be considered with great care. All right, so we've got thousands of customers using the system. And I must say, after 3 years working very hard on these kind of problems, that definitely machine learning proved to have a huge value for this type of issues, like anomaly detection, ability to learn baseline, and things like that. So that was really a fantastic milestone. Then we worked on device classification. So let me explain that use case, which again is very interesting. When you look at networks, it depends on the policy that you're using for security. You may have heard of zero trust, and we have multiple ways of approaching that. But a common use case is that when a device joins, you may allocate some rights to this device based on the nature of the device. So if this is a laptop, or this is a camera, or this is a printer or an iPhone. So the first approach is basically to ask to the device, right? What type of device are you? And there are many protocols that allow you to detect the type of device based on some self-device declaration, if you will. So you look at the DHCP option, for example, and you may say, oh, this device is trying to get an IP address and claims to be a device of a given type. But with the emergence of IoT, the Internet of Things, there are many, many devices that did not support all these protocols. So we could see the device coming on the network. We had no idea of the type of device it was. And if you don't know the type of device, you could not allocate some resources to the device in terms of accessing to some VLAN, for example. So the idea was, well, how can I use machine learning to help? And we came up with a mechanism so that we can use machine learning to improve the task of endpoint classification. So you immediately think of, oh, they're going to use a classification algorithm so that you can detect the type of device based on some input features. But in this case, there was no ground truth, right? So you could not use classification. Remember, you don't know the type of device. So the goal was to have an ML-assisted approach. And in this case, what we did was to look at many attributes of devices, unknown devices. We would group them together using some clustering mechanism. And then we would go to the user and say, you look at this cluster of green points, they look the same type of device. I just don't know what is the type of device. So could you give me some information about the type of device? Some customers, they still refuse to allocate any right to any device without knowing the device type. So in this case, you would have to go one by one, even if you have hundreds of thousands of those, and basically provide the type of device in order to allocate some rights, right? So it doesn't scale very much. So what ML would do in this case is to say, you have a cluster of 1,000 devices. I don't know what they are, but they are all the same. Just inspect one of them, and then you can give me a label. And once you have a label, you can start learning a second rule. And in this case, you can automatically classify all of the above, and you get a new rule for free. In other words, you train the rule, and then the rule can be used automatically by the engine, which was super elegant and worked out really well. The difficulty in our case was the distance. It's not really here I'm just showing a DB-scan, density-based clustering mechanism. But of course, you really need to understand what is the distance you will be using so that if 2 points in that space are close, then they are likely to be similar. So that was the biggest task of this exercise, was really to define the distance. Of course, as always, right, you want to measure the efficacy of your system. And that's really the most common question, which is, how are you measuring the overall efficacy? So in our case, we had to look at the purity of the clusters, which is a very simple one, the percentage of unassigned devices. If I come up with devices not even in a single cluster, it's not what I want. If you give me too many clusters, maybe there could be also overlapping clusters and things like that. So we came up with a lot of metrics. And that's where it's getting so complicated, because regardless of what you do, regardless of the project, the more metrics you specify, the harder it gets to really understand the efficacy of the whole system. And of course, there are tensions between the metrics. So at some point, you need to be able to look at, in this case, the purity, and you may tune your algorithm and the loss function so that you improve purity. But in this particular case of purity, you end up with many clusters. And sometimes you start to split the same type of devices across multiple clusters, and you impact stability at the same time. And each time you train your algorithm, you come up with new clusters, or you may have even devices jumping between clusters. So very interesting exercise. What I want to say to you guys today is what we've learned, as always, is that the last mile is really the one that is the most difficult. And doing a quick prototype with a data set is usually not so hard. When you want to bring it at scale and start training the system on millions of points or dozens of thousands of data sets and elements in the data set, then it's getting really hard. And that's really where we spend most of the time, is really to do that at scale. So in 2019, we also looked at something interesting, and I spent just one slide, but it's yet another fun use case to show, and this is known as the spoofing attacks. So in other words, once you know that if you claim to be an iPhone, you have access to some resources in the network, you may want to spoof your identity, well, not your identity, the device type in this case. And then, of course, you want to detect when someone claims to be an iPhone, but it is not an iPhone. So this is one type of attack. So here we use, again, a very different approach. So now the approach was a behavioral analytics approach, where you would basically train some machine learning models to recognize the behavior of an iPhone. So we had multiple models for multiple classes of devices, each for each class, using a whole bunch of attributes. And we use machine learning, we use NetFlow, in machine learning to look at the behavior. So now the idea was oh, there's a new device coming in. The device claims to be an iPhone. Let me take the machine learning model trains to recognize an iPhone. I will look at the behavior in terms of applications, in terms of, well, the whole behavior, if you will, looking at the traffic. And then I'm going to start to see if that doesn't match. So in other words, if the behavior of a device is not very close to the behavior of an iPhone, based on the model that has been trained, this probably spoofing attack. And then in this case, you can trigger some quarantine and things like that until you can detect whether it was a spoofing attack or not. So we're still working on it. We have many prototypes available, and this is very close to being in production. This was, again, a very nice application of a machine learning model. All right, so now let me move to what I believe is, to me at least, one of my most fascinating topics over the past 30 years about the predictive internet. First of all, there's so much to say about the predictive internet. So I just wanted to start with a few comments. So when we started this initiative, we wanted to really look at the behavior of the internet. And many people have done that in the past, so there's nothing new. But still, we wanted to see how we can use machine learning and some statistical properties to look at the delays and the packet loss and the jitter and many other properties of millions of paths across the internet, really to understand, if you will, the dynamics of it. Usually what people do, they look at some packet loss, they look at some delays, they use some very basic statistical analysis. Here we really wanted to go way beyond that, because the belief was that by learning the behavior, we may be able to predict what will happen in the future, as opposed to react to an event and a failure. So I'll go back to that in a minute. So we look at many things, like the variability of some KPIs. So here we see the trajectory for a given path in terms of loss, jitter, and latency. As you can imagine, if you only look at the jitter, loss, and latency, you measure it over 1 hour, you compute the average, it may look fairly stable. If you look at the granularity of 1 minute or even 1 second, you may start to capture some very chaotic path. And the behavior of such a path will impact dramatically your application and your experience as well. So we spend a lot of time looking at many types of metrics. We have multiple white papers. One of them will be published next week about the type of metrics we want to use for that, such as some Welsh metrics, some entropy and stuff like that. So we wanted to start with that. And we have found out a lot of very interesting properties. We also wanted to look at the quality of voice over the internet. So was it a fairly stable metric or not? So you might have heard of a mean opinionated score, which has been used for a long period of time. And that shows you, it's a metric that we use between 1 and 5, 5 being the best quality for voice, 1 being really bad. And we wanted to look with across the world with billions of records. We wanted to see how much it would vary. So would you have a very stable voice in a given country at a given time? And in another country, it may be really bad all the time, or would you have a lot of variation across countries, across time? So here I'm showing you the percentage of calls with insufficient quality. So the user experience score is below 4. In other words, the quality of the call is not good enough. And I'm going to show you a quick video, and you see it was only from 1 year ago, and look at what we see here. And the data speaks by itself. Whether you are in the US or South America, Europe, Africa, India, Asia Pac, what you see is that the percentage of call with insufficient quality varies all the time. So is that the good news? Well, it depends, right? If you are a machine learning engineer, or data scientist, when you look at that, you think, oh, maybe there's something to learn. And if I can learn a signal, maybe I can start using a machine learning model that would allow me to predict what will happen. And that's exactly what we wanted to do. So here I'm just focusing on voice, but of course, we look at video, we look at what we call SaaS applications like Office 365 and WebEx and many other applications, so that we can start really deeply understanding of the dynamics of the internet. All right. So as I said, this is a new world, right? We see a lot of application moving to the cloud, which is very interesting when you think about this, because just 5 years ago, networks were fairly static. You would be reaching some application in your own data center, but they wouldn't move. Now the world is completely different because the application, they are in the cloud somewhere. You don't even know where they are. And by the way, they move all the time. So the target, if you will, is not something that is fixed, is basically an application moving. And you have a plethora of technology to reach out to the cloud as well. So you have your private network, you have the public network, the internet, and you have multiple technologies to reach out to both networks, and you're trying to reach out to many types of applications. So some of them, they are located in your own data center. Other ones, they are located in the cloud, and everything is dynamic. So what we've been hearing from our customers is what matters is the application experience and the security. So I'll be focusing a bit more on the application experience here. So we want to route the traffic so that we can provide the best application experience. And you may say, yeah, but we've been doing that for 30 years. Not quite, because for 30 years, what we've done is to look at the graph. The graph would be weighted with some metrics reflecting the capacity of the link, if you will. It could be the delay, it could be bandwidth. And you would be running some routing protocol to find the shortest path. But the shortest path, according to some metric, may not reflect the application experience. So that's what we want to change. The second part is to become predictive. We haven't done any predictive routing in the past. It always has been a reactive mechanism. And this is so interesting. Why? Because if you look at all of the protocols that we have developed and the technologies, what you do, you detect a problem, you try to do the detection as quick as possible, then you try to find an alternate path, and you always are in a reactive mode. There's no learning at all. Again, I won't go back too much to the human brain, but if you look at the way, from what we understand today, the way the human brain works is that you learn thanks to experience. We now understand the mechanism of pruning of the synaptic, the synapses in the brain where you are a baby, and then the plasticity, what you call synaptic plasticity training, when you're trained to new tasks and stuff like that, how you do the planning, the prefrontal cortex. But again, I won't go there. Still, the predictive internet is exactly that. What we want to do, we want to have a model to understand the world. In our case, this is the internet. We want to be able to predict some issues, especially the application experience issues. And you want to learn and keep improving, thanks to sensing. And the sensing that the human brain uses, such as the touch and the vision and the hear, here is going to be the telemetry. And of course, with that, you can start to do some planning, and planning is done with automation. So the brain is an amazing predictive engine. When you grab a cup of coffee, you predict the shape and the weight of a cup, and then you just thanks to sensing. When you play tennis, and it depends how fast you play, but in general, by the time you see the ball is already a few meters away. So you need to predict as well. So there are very, very interesting theories on how the brain is using predictive analytics, but I won't go there today, obviously not. But talk a little bit more about the predictive internet and what we can do. So for me, there are 3 pillars. One is to be predictive and not just reactive. In other words, be able to predict there will be an issue at 4 p.m. if you use the public internet, and instead you may want to use 4G channel connecting you to another pub somewhere. So that's predictiveness. Second is the ability to look at connectivity, but also bad application experience, which is a very hard thing to do. And the third one is if you can predict, you may want to be self-healing. In other words, have a sort of trusted automation where you know that you can trust the prediction, so you may want to anticipate and readjust the network. So it's a very short video to show you here. This is what we call an SD-WAN network. So in this case, you have a branch office. The branch office is connected via MPLS or internet to a data center. You may have a local breakout to the internet, and in this case, you may want to reach some SaaS applications. That's a really typical example. Here, you have a brain of the predictive internet running in some location, and that brain is fed with a number of telemetry sources coming from the network itself, but also the user application experience. So the goal, if you will, of the predictive internet is to train models so that you can start predicting when there will be an issue, when there will be a bad application experience, and could be via even multiple cloud as well. So this is what we want to do. If you guys are interested about that, I published a few months ago, and I keep refreshing it, by the way, some articles going through that. It's only 6-7 pages. There will be multiple revisions of it coming up soon. We're using a plethora of technologies here. We have our own models. We may be using some LSTM, state transition learning, and what is really fascinating to me is the results and what we see. So is it a beautiful idea? And I'm showing you some nice videos. No, that's not the case. That's something we've been testing for almost a year on more than 100 networks with small scale, very, very large scale, multiple regions in the world. And here I'm just showing you some heat maps with the number of minutes with violation of service level agreements. So in other words, a bad experience that were avoided thanks to the predictiveness of this engine. When it is red, it shows that we managed to avoid issues, a lot of issues. I know this is a little bit of a funny color code because red should look like bad. In this case, this is good. And what I wanted to share with you was the dynamics. So the x-axis shows you the time. The y shows you multiple regions in the world. And you see here a network where, regardless of the region, we have a period of time where there's not much to do, there's not much to predict, and sometimes you have really, really a lot that you can avoid in terms of issues. In the second network, you see some areas where there's not much to do, areas where there's a lot to do. You see some seasonal paths, you see all of the above. So why is it so interesting? Because even for a given network, you show that you need to constantly do some learning. And the explanation for that is simple. The internet is extremely dynamic. And one day you may have some really good experience. The day after, it may be a little bit, a little bit difficult, I would say. It could be because of bottleneck. And so we're going to start learning all of these patterns. And the usual question that I have is, how much can you predict? And what is the accuracy and stuff like that? So what I want to say is basically that today we're predicting zero. We're not predicting anything. So the goal for me was to say, if I can avoid 5% on all of the issues, I would be extremely happy, because 5% of all of the issues you may have across the internet is an enormous amount. And actually, we passed, by far the 5%. But it's just to show you that the way we tuned the system was to have a low recall, but high precision, because I cannot avoid to have false positive in this case. So that's exactly what we did. We found out ability to predict high latency that were seasonal. We managed to see sometimes unexpected behavior, like MPLS being worse than the internet. That does happen. Sometimes we detected some high jitter, which was a bit of a surprise because we thought that jitter was very noisy. You may remember the first slide I was showing jitter may be noisy, but we managed to predict quite a few things here. Okay, so that's a typical example. At least I wanted to share one with you. So in this particular case, what do we see? So here we see that was a link between Netherlands and Italy. We could see that we could have avoided about 82% of all of the service level agreement violation in a month. And you know these spikes here? You see that they were predicted by the algorithm. And in this case, the algorithm, hours in advance, said, look, you will have an issue on MPLS, you may want to switch to the business internet. And I know you may say, well, maybe this was handpicked. And in this particular case, it was obvious. You can imagine that we looked at hundreds, thousands of such predictions. And at some point, we had to admit that we were on the right track. And we could detect a lot of things. And we had very high precision. And in some cases, we may even have some really good recall at the same time. So that leads me to the conclusion. Just a few things that I wanted to say, right? If you look back, what are the real challenges? Usually the one question I have is, what is the algorithm that you guys are using? And I don't think this is a real challenge. Of course, you need to understand the algorithmic part. You need to be aware of the math behind the scene. This is very important. But the real technical challenges are really to define the objective function, and even what is a false positive or true positive. If you go through some classification, you may say, well, this is obvious, but it's not so obvious. Of course, the famous example of recognizing a dog versus a cat is there is a ground truth. You cannot be in the middle. But what is a failure? Maybe a little bit harder to do, but start with that, spend a lot of time on a good data set, remove the noise from the data set, make sure you have some good objective function, you really understand what you're trying to do, and then you can start going through the system optimization. I would really say start with the most simple, the most naive approach. Have a look at the statistical modeling as well, because it may be very, very useful as well. And knowing what machine learning can and cannot do is the key, absolutely the key to know a priori whether you're going the right direction. So in some cases, you may have an intuition that this is the right direction. You may have to fail fast and say, no, there's no signal, and that's totally okay as well. So really my last conclusion was, I believe that ML is proven to address a broad range of use cases. We talked a little bit about security, wireless networks, classification of devices, and the predictive internet. As a matter of fact, the network and the internet have never been so dynamic because of the type of connectivity, because of a number of service providers and the geo and all these things. Application experience is getting really the top of mind issue for every single IT company. And I believe that we are on the way of a new wave, which is really called the predictive internet. After 40 years of doing a reactive system, and machine learning AI will play a fantastic role. So stay tuned. There will be way many more results to be shared with you, many other applicability of machine learning AI for the predictive internet. So that's how I would conclude my talk. Yes, I know that we have, I was given 60 minutes. I took 80, not 80, 58 minutes. I don't know if we have any question that you would like me to address. You guys can join me on Twitter. This is JP Vasseur. And you can also drop me an email at jpv@cisco.com. I'm always happy to answer questions and see your interest. So Jess, do we have any questions for us today?
Yeah, so I've got some of my own, which we can kind of chat through. So I'll just, if anyone does have any questions, please pop them into Q&A. I know sometimes, a lot of you have to drop off because it's 2 o'clock, but thank you for joining. And if you open the chat, JP, you can see lots of people already thanking you. Alex Minolti, thanks, JP, great talk. Nor, fantastic talk, thanks, JP. My head is jam-packed with powerful insights and I'll need the day to process. Absolutely right, my brain is melting. Anthony, thanks. Tara, wow, brilliant talk. Anwar, great talk, JP. Thanks, Jeffrey. Thank you, it's very interesting. And Tom, a brilliant talk. Thank you very much. So yeah, if you do have any questions, please pop them in. So JP, you mentioned about the predictive internet. Were most of the recent major outages actually predictable then?
Yeah. It's a very fair question, right? So, I think the honest answer is, if you look at these events in particular, most of them were one-off, right? So if this is a one-off event, there's no signal, a priori signal. So I don't have all of the details about what happened. I guess that I see the events that have been, you've been referring to, but there's no magic secret sauce, right? You need to have some signal first of all. So sometimes people say, oh, but can you predict the Black Friday? Well, you need to see quite a few Black Fridays, so it may take a long time before you start. You can really predict what will happen on Black Friday. So when this is a one-off event, or you have a very unbalanced data set, which is always an issue, and you're trying to predict rare events, it's always very challenging to do. When this is pure one-off, there's no way you can learn before. But in many, many cases, we can learn from the past, and we don't even know that we can learn from the past until we do it.
Yeah, no, definitely. I've got just two more if you've got 5 minutes.
Yep.
We'll run over a little bit, and then obviously, if anyone has any questions, pop them in the Q&A. I think most people are like me, and they're going to have to watch this recording back to kind of digest everything that we've just learned in the last hour. So I've got one is, what are the main challenges you faced during the development of an AI-centric product in your industry?
Yes, the ability, I believe, the ability to define, that's why I was saying in the end that it's so important to spend time on the objective. And I know sometimes, you have a team and everybody believes that they have a good understanding about the problem to solve. And as you move, you start to understand that, well, it's not so easy to determine what you're really trying to achieve. So for example, I was talking about the false positive, but you need to understand when you look at failures, on a given path, is a failure the fact that you cannot talk for 1 minute or 1 second, or is it that the quality of service will not be good enough? So the ability, if you will, to really understand what it's trying to achieve, and the metrics, the explosion of metrics, it's so easy to come up with metrics. And at the end, you look and you say, oh my gosh, I've got 20 metrics, and it's always great, right? You've got, for some metrics, the results are good, for other metrics, they are bad. And then you start spending a lot of time and say, is it because the data is not clean enough? Is it because the problem has not been understood at the beginning? Is it because I don't even know what I'm trying to achieve? And people tend to believe that we spend time on the tuning itself. This is a fun part. The tuning is really the fun part. And if you have done a good job at looking at the telemetry, the problem, then the rest is fairly easy to do. That's really what I would say.
Cool, perfect.
Make sense?
Yeah, definitely. And we've got a question coming from Noor. Hey, Noor, thank you for joining. Hopefully see you on the 27th if you are coming. We'd love to catch up with you. Will Cisco move to prescriptive analytics in the future? So are the current predictive analytics used for automated or augmented decision-making or actions?
Yes, it's a vast topic, to be honest with you. So yes, we are definitely looking at it in multiple use cases. So when we say Cisco, we have so many things, right? We have a collab where we use a lot of natural language processing and stuff like that. So yes, we're looking at that in multiple areas. It's a little bit too soon to tell you more about it, but yes, we are. But Noah, if you want to reach out to me, you're very welcome. I'll give you more insight about what we're doing in this area.
Secret. It's coming soon. Stay put.
New stuff coming up.
Yeah. So I'll do one more because I'm conscious of time, and then we'll kind of wrap up, I guess, more of an opinion piece. But would you say that machine learning and AI will replace all existing systems in the network industry?
No, that I know it will not happen. And believe me, I'm leading a team doing machine learning at Cisco. So I spend more time saying no than yes. Why? Because it could be another kill.
Yes.
That's it. That's all I would say. That's why I kept pushing for statistical models and say, look, you can do so much with really good statistical models. If you really understand the KPI, look at the CPU of a computer. Well, you don't want to go too high. You just put a threshold. You're good to go. You don't need. Yes, you can always come up with a model that will tell you what is the expected CPU usage and stuff like that. But at the end of the day, you only care when you go too high. So, just start simple. That's what I would say. And that's why I believe there are a majority of problems where machine learning AI is not needed, but there are also cases where you don't have a choice, and that's good. You look at the prediction, without a machine learning AI, there's no way you can do predictive analytics. So that's one of the examples where there's no alternative, and we love it because we can do a lot of cool stuff with it. That's the way I would conclude this talk.
That's a good place to end. Cool. Well, Thank you, JP. It's been a pleasure to have you with us. And you know, I literally feel like my brain's exploding. So I'm going to probably have to watch that back. There's a lot of information in there. I'm so grateful to have you. And hopefully we'll have you back, you know, in the festival again, because I think the session was absolutely brilliant. Thank you for everyone in your words in the chat. JP, if you want to have a read through, there's loads of people in the chat saying thank you. It's nice to see, you know, see all the people there. So yeah, thank you guys very much.
Great. Thank you to all of you. Take care. Stay safe.
Thank you, everyone.
Bye.
Bye.